record original size. All right. Fine. So today we are going to start with next topic, that is inductance. Right? Inductance. So now let's recall what is inductance. So if you remember, in chapter 1 we have discussed, we have taken two spheres.
Yes.
Right? And they were in physical contact.
Hmm.
We had put a positive source over here, and because this was a metallic sphere, so all the electrons were attracted towards this region, right? And the holes were deflected on the other side, right? And when we have separated this, we got two bodies, two different entities with negative and positive charges.
Yes.
Right? To which we define that this is charge inductance. Charge inductance. So basically we say that whenever there is no physical transfer, right? Right? But you are getting that property in that particular material, right? You call that is inductance. Okay. So let's understand the meaning of this and how it is going to depend on a system. Now, inductance means you simply say that you have a coil. You have a coil. Where is solenoid is going to be acting as a inductor. Okay. If you have a straight wire, it can never act as an inductor. Okay.
Yes.
Okay. Fine. So now, if in this particular coil, if you allow current to pass, that means I amount of current is passing. Okay. So magnetic field will be created. That is all right.
Hmm.
And that value is B is equal to mu 0 and I in a solenoid.
Yes.
Now, if you are allowing current to pass, what is going to change inside the coil?
There will be induced current. Induced
Why?
magnetic field will be there.
Okay. So no, we basically know that if you are going to supply current, you will get magnetic field.
Hmm.
Right? So to understand, you can simply stay step by step that initially I was equal to 0. So B was equal to 0.
Yes.
When now this I is increasing, so is your B. After a particular point, your I will become max. That means it will saturate, it will become steady, right?
Yes.
And your magnetic field will become max, right? After that, there will be no change.
Hmm.
Okay. We also know that if you are changing magnetic flux, so you will get a current, that is EMF will be induced.
Yes.
Okay. So what we now basically say is that you can induce a current, right, by simply changing the magnetic flux inside this coil.
Hmm.
Right. Now, if you place another coil, right? If you place another coil somewhere over here, for example, right, next to it, neighboring, right? So there is no physical contact.
No.
Right. We have seen this in that earlier examples, right? When you have coils and coils neighboring, right? Right. So
Yes.
when magnetic field is changing from here, current is
Hmm.
induced in this particular coil. Fine. Now, so in this case, we say that your magnetic flux, right, is depending on current. Right?
Hmm.
If you remember the current over here, this will lead to magnetic flux in this coil.
Yes.
All right. Fine. So similarly, can we now say this way also, that if it is d phi by dt, that it will be proportional to di by dt.
Yes.
Okay. And if you have number of turns, right, that will be directly multiplied with n.
And
So can you write in this case that n into phi b is proportional to I?
yes.
So you have passed current from this coil, right? And here you have n number of turns, and this n number of turns has led to n into phi b.
Hmm.
All right. Now, so this relation, what you say is that because the current was flowing and because of that current flow, you are getting some magnetic field or magnetic flux in another coil. Right? If you remove the proportionality sign, you call this as inductance, L into I, or it is M into I. Now, that is between two coils, two different coils. I will define
Yes.
over here this term as magnet. No, just a second. I will use symbol M. That is mutual inductance. That is mutual inductance.
M is a constant.
Yeah, M is the proportionality constant, and this is actually called as inductance. Right? Now, inductance can be of two types. Basically, what we say is inductance is of two types. One is, in this case, you are getting, because of this, you are getting inductance in this. Right? And in
Yes.
another case, we'll say that you have the same coil and by its own, it is inducing something. Right? Induction process is taking place in self body. Right? There is no second body, but it is occurring
Hmm.
because of itself. We will see that. Okay. Unit of this inductance is Henry. Okay. And that is a scalar quantity. That is a
Yes.
scalar quantity. Okay. Can you try to find out the dimension of M? Can you try to find out the dimension of M? Can you help me with
M.
that? Yes, MLT.
M. Uh, N is
N is number, so that won't count.
yes, and then flux.
Okay, so
Flux
how will you write
value.
flux?
Which value to take? Like BLX.
Sorry?
Uh, Flux value. Like flux is equals to BLX. Through BLX, we can find the dimension.
Okay, B, L, X.
So
Okay,
B is
that upon
magnetic.
I, that is M. Now proceed ahead.
Then L is length. L. I can be
L is
written
length,
as Q by T.
Q by T.
No, sorry,
So,
sorry. Wait. No, it
see,
was
try to understand, you have to bring your equation in the form of MLT. Okay, and maximum you can have current, that is ampere.
oh yes.
Right. So how will you proceed?
After that, we can find what was X.
X was your distance.
It will be also so it will be L square for LX.
Okay, fine. So it will be L square. That is first point. Good. This you can emit.
Yes. Then for magnetic, now we have to find for magnetic field. Magnetic
Yes.
field. Magnetic field is force into charge into velocity. Yes,
Yes. Yes. Proceed. Give a try.
we can write magnetic. We know that force is equals to QV into B. We can use that formula. For
Repeat
finding
again.
magnetic field,
For finding magnetic field, B will be
we can, like, we write force is equals to QVB, right? So for and then we can find B is equals to F force by QV.
okay.
Then force formula is MLT minus 2 upon for charge. For charge we can write
Mhm.
Q is equals to I by T. So I T minus, and then V is LT minus M L. It will be M T minus 2 I minus 1. ML raised to power.
M.
T minus 2, matlab T raised to power
Mhm.
minus 2, and then
Okay.
I raised to power minus 1. This is for magnetic field, B.
Okay. This is for magnetic field. Okay. Can you also think in simple way that you know that F is what? BIL.
Yes.
Can you solve with the help of this?
Then B is equal to F by IL.
So, okay, B is equal to F by IL. Try to understand in this particular format. Okay. You are supposed to find what? Inductance, L or M, right?
Yes.
So that is what? Flux upon current.
Hmm.
If you focus back, right, it is what initially we have said that this is the format,
Hmm.
right? So that is magnetic flux divided by current, and flux is what? B into A
Yes.
divided by I.
Hmm.
Right? So B is what?
Magnetic
F
field.
upon I L
Hmm.
into F upon I L into area upon I. Okay. So this will
Yes.
be force. What is force? That is
MLT
M ml T
T minus 2.
minus 2. Okay. What else you got?
We can
Into
write area L square.
area, that is L square. So area and this length, right? You will get only L raised to 1.
Yes.
Okay. And divided by ampere square.
Ampere. Yes.
So what your final answer is M L
L square
square
T
T
minus.
minus 2 into A raised to minus 2. Alright?
Hmm. Yes.
Okay, fine. So let's move ahead. Okay, fine. Now let's consider what is mutual inductance. Okay, so we are saying mutual inductance. All right. Now, what you actually say? Okay, mutual means we have already defined it is because of body one into body two.
Yes.
Okay. Right. So let's take one coil over here. Okay.
Hmm.
Let's take another coil inside this. All right. You can consider a system that one spring into another spring.
Hmm.
Okay. Let's also consider that this length is same for both. So L. Okay. The outer one is suppose S2 and the inner one is S1. Okay.
Hmm.
Corresponding radius is R2 and corresponding radius is R1. Okay. Fine. Number of turns per unit length is N1 and N2 over here, and it is N1 over here. And length is same for both. Fine. we basically understand what the inductance is, what that you are supplying current in one coil, because of that there is some induction of magnetic flux in another coil. That is what we have said. So we write that N into phi, right, in any flux, right, that is M times current in another coil. So if you write this is 1 and 1, so this will be 2. Okay. So you are saying simply that current passing through second coil will produce some inductance of flux in the first coil.
First, yes.
Okay. That is called as flux linkage. That is called as flux linkage. All right. Now, same way if you want to write it reverse, so you say that in second coil it will be N phi 2 and that will be M. It will be I1. Okay. This M you can say that this is M21 and this is M12. We are going to prove that it will be same in this particular case. Fine. So let's take a simple example. Let's take a simple example and understand that you are allowing current to pass through the outer coil. That means the blue coil, the larger coil. Okay.
Okay.
So current I2 is passing through the outer coil. So flux will be linked in first coil, inner coil.
Yes.
So N phi 1 that is equal to M12 into I2. Okay. Fine. What is the magnetic field produced? Okay, so let me just highlight this. Okay. So what is the magnetic field that is produced inside this entire solenoid? What is that formula?
U naught Ni.
Mu naught Ni. All right. So you will say that it is mu naught Ni. All right. Now you want to calculate this value. Okay. So
And which value?
N151, right?
Okay.
Because that is the flux linked over there.
Yes.
Now, this entire portion, right, bigger solenoid is having magnetic field in entire area, right?
Yes.
Fine. Now, what is the flux linked with this inner coil? It is very similar to your ice cream party. For example, when you go in a party, right, in a marriage reception, what happens? You have a big cane, right? So what
Yes.
you have one ice cream cane, okay, and so this is filled with entire ice cream. Okay. Now, if you take another cylinder or another scoop, okay, and you just put it inside, right? So even though here the ice cream is there, right, entire thing is filled with ice cream, but you are going to get your ice cream only in this area,
Yes.
right? So flux enclosed or flux linked with the inner coil is only this much, the area of the inner coil.
Yes.
Okay, fine. So you say that here flux is what? So I will calculate N151 separately. So that will be equal to what? Number of turns first of all. Okay. So number of turns is what? It will be N1 into L, because we know that N is the number density
Yes.
per unit length, so multiply by total length. Okay, that is N1. Flux, that is B into A.
Yes.
So B into A. Okay, what is your effective area? That is pi R1 square.
Yes.
So I will write area first. So pi R1 square. Right? And what is magnetic field? That is mu 0 into N2 into I2, because magnetic field is because of the second coil.
Yes.
All right, just a second here. This I have to rub it I1. Hmm. So you are having I2. Okay. Now this is the flux linked with the inner coil, smaller coil, when
Hmm.
you are allowing current to pass through the outer coil. Now this can be understood as, okay, so you can write it N1 N2, okay, then mu 0. Okay, so N1 is done, N2 is done, mu 0 is done, pi R1 square into I2 into length. Okay, this is the value of N1 pi 1. And this is nothing but equal to M1 to I2.
Yes.
Okay, fine. Now let's make it reverse. If you are supplying current in the inner loop, that means the smaller one, right? So you
Hmm.
are allowing current to pass through this one. Okay.
Okay.
So what does this say? Right? It is saying you simply that current is passing through the inner coil. So magnetic field will be produced where? Magnetic field will be produced where?
We are talking about the inner loop, right?
Right, that is S1, smaller loop.
And current is going inside or out, is coming outside.
That is okay. That is okay. Whether it is going inside or outside, right? That will just define the direction. That we are not bothered about the
Yes.
direction. Okay. Let's consider the direction of current as say outward, right? So magnetic field will be rightward,
Right.
right? So
Yes.
magnetic field will be going this way.
Yes.
That is all right. Now, so you will say over here as, let's say,
It is also a solenoid, so B value will be that only U naught mu naught Ni.
okay, fine. Now let's understand over here. Let's come over here. Okay. So you say that because current is passing through the inner coil. So you will say it is M21 and current is passing I1. So you will get N2 into
Two.
N2 into phi 2.
Yes.
Okay. Now, what does this says is you have to calculate this value.
Hmm.
That is what?
That
So you will
N
write N2 phi 2 is nothing but, what is
N2L
N2? N2 is what? N2, well, good. Flux,
NB.
that is B into A.
Yes.
Okay. Now consider, now tell me, the magnetic field is because of the first coil. So the value of B will be what?
It will
B will be
this
mu 0 N1 I1.
I1.
Okay.
Yes.
And now what will be your effective area?
Pi R1 square.
Pi R1 square. Exactly. Right? Pi R1 square. Why pi R1 square? Because you have your cylinder of ice cream.
Yes.
If you take a bigger cone, right, or bigger cylinder, right, the ice cream content is this much only, right?
Yes.
Right? So effective area will be that much only. Okay. So it will be pi R1 square. Good. So now let's move ahead. Okay. So this value is what? This is N5. Now, so you can write this as M21 I1.
Hmm.
So if you compare, just compare it and we'll cancel out. Okay. So here I2 and I2 will cancel. Here I1 and I1 can cancel.
Hmm.
Okay. Now if you compare this equation 1 and equation number 2, right side is M12 and M21.
Yes.
So right side is M12 and here it is M21. Okay.
Hmm.
Now just compare the left hand side. It is same or not?
Yes, it is same.
right? Same, right? So you are getting mu 0 n1 n2 into pi r1 square into L.
Yes.
So from here we can conclude that it is m12 is equal to m21.
Yes.
Okay, fine. So this is what it is saying, that because of one current flowing in first coil, you have inductance in second coil. Okay, fine. So you'll call this is same. It won't make any difference. Okay.
Hmm.
Okay. So this is called as flux linkage.
So,
Okay.
but in that above uh, N5, we said that M is proportionality constant.
Yes.
So here we have taken out its value.
Yes, we have derived its value.
Okay.
Okay. And this formula is normally applied for the case where both the coils have same length. Okay.
Okay.
The length should be same. Fine. Now, that is one thing. If you insert a iron rod, right? That means
Hmm.
if you insert another rod inside that spring, that is if you insert a metallic refill, right? So here we know that your mutual inductance will go high and it will be multiplied with mu r. So it will be mu r times mu naught into n1, n2 into pi r1 square into L. We know that magnetic field was getting increased, right? If you are taking a solenoid, right? And inside that, if you are inserting a rod, we have seen this in the
Yes.
earlier, right?
Hmm.
Fine. This is what you call as mutual inductance. Inductance because of first into another,
Hmm.
right?
Yes.
Fine. So in the next class, we are going to see about self-inductance and we will also see about its numerical section.